And my intent for this is let's go ahead and get to the mechanical procedures. So there's a lot of theory, and in my opinion, the first 3 sections, the first 2.5 sections of Unit 5 are the most challenging and the most important from a theoretical standpoint. Then we get some nice results that allows us to do a bunch of computations very quickly. But what sometimes happens is we spend so much time on the theory, we don't get to the practical applications of that theory until the end. So what I'd like to do today is we're going to just operate with some of these ideas without fully understanding them. We're going to learn how to do some problems without fully understanding why what we're doing works. But that gives you kind of a chance to get exposed to these new operations, and it allows you to go ahead and start doing a lot of the review for the final and whatnot. And then we'll flush out the details over the next 3 days. Okay, so I want you to pay attention to this word net area, or I guess pair of words, net area, as opposed to the word total area. So we will be making a distinction between the two. Okay? So if I talk about total revenue versus net profit, that might kind of give you a sense of it, right? So total revenue is how much total you brought in, but yet your profits may be less than that once you subtract your costs. That's kind of a nice analogy for what we're doing here. So our goal in Unit 5 is to learn how to find areas underneath curves. That is the second half of calculus. Shoot, we've only got 2 weeks left. Well, we've done all the heavy lifting, which is really nice. Okay? It turns out that the first half of calculus is going to help us quickly answer questions from the second half. Okay? But this second half of calculus is concerned with finding the area underneath the curve. So let's say we have a function that looks something like this. So here we've got this function f of x. Okay? My goal is to determine the net area underneath this curve and the x-axis. Okay? So there I've shaded one particular region. Okay? Here I've got another region, and here I've got another region. So our goal is to determine what is the what is the area underneath this curve. So when we do this calculation, we expect to get what type of object? We expect to get a number when we compute this. Okay? So this is like when we said what's the derivative at a point, we got a number. When I say what is the area underneath this curve, we expect to get some number that represents the area underneath this curve. One thing that's going to be a little bit tricky is to realize that these two regions right here, when we do our calculation, when I'm talking about net area, those two regions right there get a positive area. Those two regions right there are going to get counted as positive versus this region, which is going to get counted as negative. All right. So again, we are we're kind of diving into the deep end here. So this is going to feel a little disconcerting. Pretty soon we'll move into just calculations. And at a certain point, the calculations will start to feel familiar, even though we don't have all of the theoretical framework for this yet. Okay, so how are we going to talk about this area underneath the curve? The notation that we're going to use, and we'll justify this later on today and tomorrow on Monday. But the notation that we're going to use, in fact, let's go ahead and let me go ahead and label. Bring out the colors here. Let's go ahead and label this as. Oh, that doesn't show up. Let's go ahead and label that as A right here, and this as B right here. So we've got this x value A and this x value B. Okay. So the notation that we're going to use is we're going to say that the integral, right, the net area is equal to the integral from A to B of f of x dx. That's the notation that we're going to use. Does that notation look familiar? Oh, folks, I need a little more interaction today. Does that notation look familiar? Yes. Oh yeah, doesn't it? Right? We're using this integral symbol. Remember this integral symbol? Okay, what did this integral symbol stand for in the last unit? It stood for take the antiderivative, or the antiderivative of a function, right? How is this different from the notation we used in the last section? Yeah, so we've got this A and B. Okay, so this notation right here stands for the net area between f of x and the x-axis from x equals a to x equals b. That's what that notation stands for. I haven't given a name to this object yet. We'll name it when we get into section 5.2, but let me just tell you the name right now. Okay? When we didn't have a and b, we call a and b the limits of integration. When we didn't have our limits of integration, when it looked like just this, without the a and b, we said that's an indefinite integral, right? We called that object an indefinite integral, which stood for the antiderivative. Okay? We're going to call this object then a what? We're going to call this object a definite integral. And what does the definite integral stand for? The net area. Okay? So everybody, what does the definite integral stand for? The net area. Okay? We're going to learn how to compute this today. We're going to jump straight to the main result. We're going to learn how to compute it today. Normally we spend 3 days learning kind of a backwards procedure, and then we make a nice result with the fundamental theorem of calculus, and then finally we get to actually computing this. It's sort of like I'm skipping over the limit definition of the derivative, and we're going straight to derivative rules, which is a silly thing to do because you don't understand what the derivative is until you've looked at it through the limit definition. Kind of the same idea here. Okay, so we're going to learn soon the fundamental theorem of calculus. Okay? And there's two parts to it. The first part does the walking, the second one does the talking, I guess. The first part does the heavy lifting, and then the second part is the elegant result that allows us to do a lot of computations very easily. Okay? So the second part of the fundamental theorem of calculus states this, that the definite area, or the definite integral, can be evaluated this way. So it says that if we want to compute, what is this object right here, folks?
Net area.
Yeah, everybody, what is this object right here? The net area underneath the curve. If we want to compute the net area underneath the curve, how are we going to do it? We're going to take an antiderivative of that function, right? This function right here, the integrand. We're going to take an antiderivative of it, evaluate it at the upper endpoint, evaluate it at the lower endpoint, and then look at the difference between the two. Okay? At this point, you should be saying, I have no idea why you just wrote that, and that's okay. We're going to fill in the details later. Okay? But that's going to be our tool for computing the definite integral. Okay? So, how do we compute the definite integral? By finding an antiderivative and looking at the difference between the two endpoints. I'll give you some insight into that later, but for right now, we're just going to get started with the procedure. Okay. So let's say I ask you to find the area of this shaded region right here. So let me draw a little picture here. We're going to have a quadratic. Okay. And let's see here. This is going to be the function f of x is equal to minus x squared plus 4. Okay. So that means that this function right here is going to have x-intercepts at 2, 0 and minus 2, 0. Okay. So in this first problem, I want us to compute this area right here. Okay. All right. So let's first represent the net area underneath this curve, this shaded region right here. Okay. How are we going to represent this? We're going to represent it as the definite integral from x equals 0 to x equals 2 of f of x, let me go ahead and put in let's go ahead and plug in the function here, of minus x squared plus 4 dx. Does anyone have any questions about what I just wrote up there? So here's my function, right? The integrand is the function that I'm working with. What does this entire expression say? It says compute the net area underneath this function from where to where? From the lower limit, which is 0, to the upper limit, which is 2. Why is the lower limit 0? What do I mean by that? Yeah, if we look at where did we start computing the area? It was right here at x equals 0 in this problem. Okay. So we are going to once we break after the break, we're going to go back to section 5.1 and we're going to learn a very rudimentary way for calculating this area using something called Riemann sums, okay? Which will be our building block for where we want to go, and we do have to do that. But for right now, I've already spilled, like, you know, we don't have time to watch the whole TV show, so we've already, you know, let out all the spoilers, and so we're just going to jump to the main result. How do we compute this number right here? Okay? And by the way, I do want everyone to look at this object. I'm going to circle it real quick. This object right here, what is it? What type of object? It's a number. What does that number stand for? Area underneath the curve. So it is important that you look at that thing and you see a number. Okay. How do I compute that number? I'm going to take an antiderivative of this function. What's an antiderivative of this function? How about minus 1/3 x cubed plus 4x? That's an antiderivative, right? Okay. And then what I'm going to do, and this is the notation we use, I'm going to tell myself that I need to evaluate this because the fundamental theorem of calculus part 2 said find an antiderivative, evaluate it at the two endpoints, and then take the difference. Okay? How many steps was that? That was a lot of steps. Find an antiderivative, evaluate it at the two endpoints, and then take the difference. That was a lot of steps to do at once. Most of us can't do that many steps at once. Specifically, finding an antiderivative is a tough step. So we just do that in one step, and then we remind ourselves that we're going to evaluate this at x equals 0 and at x equals 2. Yeah, Daniel.
So because it's an antiderivative, do we add on the c?
Great question. So the statement here, we'll justify this later. That's a really good question. Where did I write it? Is any antiderivative. Okay. So specifically, you usually pick the antiderivative where the c value is 0, so you don't have to write it. Now, I could put plus 552 here, but then when I look at the differences, the 552s will cancel, so there's no reason to pick any other antiderivative. So it's not the antiderivative. It didn't say the antiderivative, it's any antiderivative. Yeah, so it's a great question. Now, still, if I give you an indefinite integral problem, I am still asking you for the family of functions, in which case you still need the c value. Okay? We'll look at that as we go through some more examples. It's a good question. So no, we don't need the c here. Okay, so let's actually do this calculation. Okay? We get minus 1/3 times 2 cubed. Let's see, I'm going to run out of room here. Let me come over here. So this is equal to minus 1/3 times 2 cubed plus 4 times 2 minus 1/3 times 0 cubed plus 4 times 0. Okay. How did we interpret this notation here? So I gave an antiderivative. To answer Daniel's good question, I picked the antiderivative where the constant was 0. Okay. And then this reminds me to evaluate it at the two endpoints. Where did those two endpoints come from? The original definite integral. Okay? So does everyone see what I did here? Here I took, in this expression right here, I took that antiderivative, and what did I do? I evaluated it where?
X equals 2.
At x equals 2, that upper endpoint. And then what did I do here? I took the same antiderivative and I evaluated it where? At x equals 0. Okay? Now all we need to do is finish crunching this number. So let's see here. This gives us minus 8/3 plus 8 minus 0, right? This whole expression on the right evaluates to 0. Is everyone okay with that? Okay. So let's see here. Let's clean this up just a little bit more. Minus 8 thirds plus 8, so that'd be 24 thirds minus 8 thirds, I think gives us 16 thirds. All right, what does that 16 thirds refer to?
The net area?
The net area. What do you mean the net area?
Underneath the curves?
Yeah, it is the quantity of this shaded region. The quantity of that shaded region is 16 thirds. If you wanted to carpet that shaded region, you would need 16 thirds square feet of carpet to fill in that shaded region. Okay. Are there any questions on that? I don't expect you to have mastered this just yet. We're going to get a lot more practice with this, but I want us to, this is a great time to talk about the concept. We've got a curve, and we're looking for the area between that curve and the x-axis on some interval. Okay? All right. I'm going to have to put this on another page. Yep. All right. So, let's find the area of this shaded region. We're going to work with the same curve. But this curve continues downwards. Okay? And here's 3, here's 2, here's 1. We're going to find this shaded region right here. Okay? So it's the same curve. This is still the function f of x is equal to minus x squared plus 4. Is our answer, so this is my first question for you, is our answer going to be more or less than 16 thirds?
Less.
Why is it going to be less?
So the shaded area under the x-axis.
Exactly. So remember when we put up when we first defined net area, and this is the word net area. We'll worry about the total area question later. Okay? When we first defined net area, we said this region would get counted as positive, and then this region gets counted how? As negative. So we should get a number smaller than 16 thirds. Okay? Let's find out exactly what we get. Okay? So I'd like everyone to set up the definite integral and then check with your neighbor. Okay? Don't worry about evaluating it yet. Just set it up, check with your neighbor.
I don't get how that part on the bottom is beneath the curve.
What's that?
How is that beneath the curve?
Well, so it's between the curve and the x-axis.
So
Maybe
wherever the
between
curve
is a better
leans-
word. What's that?
So whichever way the curve leans.
Mm-hmm. Yeah.
So if it was a circle, it would be on the inside.
If it was what?
A circle, it would be on the inside.
Depends on where the x-axis is in reference to that circle. Yeah. Yeah, we'll look more at that. We'll get more into that when we start distinguishing between net and total area.
So there'd be two separate problems. Yeah, I think so.
Okay. So here we go. Here's our definite integral. It's going to be the integral from x equals 0 to x equals what?
3.
3 in this case. Okay. Of our function taken with respect to x. Okay, are you remembering to write that dx every time? Folks, when you draw a picture of a car, do you put wheels on it? Yeah, when you write a definite integral, do you put a dx on it? Yeah. Okay. All right. We'll talk more about that soon, very soon. Okay. All right, so this is the definite integral from 0 to 3 of minus x squared plus 4 dx. So far, nothing new is happening, right? Okay. An antiderivative of this. Okay. And in fact, let's just do this to answer Daniel's question. An antiderivative of this would be 1/3 x cubed plus 4x plus 9. Normally, we wouldn't put that plus 9 there, right? But I just want to show you what happens. And what are we going to do? We're going to evaluate this from x equals 0 to x equals 3. Okay? Folks, I will never, let me just clarify this. If you get to here on any one of these problems, you are at 4 out of 5 points, or 5 out of 6 points, or 8 out of 9 points. Okay? What is this next step? It's crunching numbers. Okay? Please, does it matter that you guys as calc students know how to crunch numbers? Yes. Okay? But a lot of times I'll have students spend an hour going from here to the correct answer. That's an exaggeration. They'll spend an hour going from here to the correct answer, and that was kind of a waste of time because I'm more concerned right now of you getting the procedure down. Okay? So will these often involve messy fractions? Yes. How come? It's very hard to avoid them. How come? Because of our power rule. What does the power rule always do? It introduces division, which often introduces fractions. Okay? So anyway, let's not worry too much about crunching this, but we'll crunch it together. Okay? So this gives us minus 1/3 times 3 cubed plus 4 times 3 plus 9 minus 1/3 times 0 cubed plus 4 times 0 plus 9, which cleans up to the, let's see here, that would be minus 9 plus 12 plus 9, I think. Double check me. Minus 0 plus 0 plus 9. Okay, so it gives us minus 9 plus 12. And then here I want to emphasize, here was that plus 9 from that constant that we picked. And then we get a minus 9 also from that constant that we picked. So you see that the choice of, if we put a constant there, it's going to always add out by this procedure. Okay? So we always just pick an antiderivative with the constant being 0. That's the best choice. Okay? So what do we end up with? We end up with an area underneath the curve of 3. Okay? How does that relate to our 16/3 from before? It's a little bit smaller. Okay, I want to keep doing this just to get a little more comfortable with things. Okay. So let's do it again. We're going to work with, for one more time, we're going to work with this same function, this same parabola. This time I'm going to do this. Okay. So this was minus 2, this is 2, and let's find, this is our curve, f of x is equal to minus x squared plus 4. This time let's do the area from minus 2 to 2 of f of x dx. Okay, I'd like you to crunch this. Go ahead and do it. Okay, work with your neighbors. Okay, talk amongst yourselves, but I'd like you to crunch this. So we end up with the antiderivative from minus 2 to 2, or the definite integral from minus 2 to 2 of minus x squared plus 4 dx. Did you remember your dx? Folks, what I'm putting up on the board, I mean, maybe you wouldn't write this step, but maybe you would go straight to here. But other than that, I'm doing this in as short of steps as possible. Okay? So the next step is to take the antiderivative. So that would be minus 1/3 x cubed plus 4x. Now what? I mean, this is a what type of object? What did we say this was? This was the definite.
In that area.
This is the definite integral, so this is a net area. So what type of object is it?
Number.
A number. What type of object is this thing over here on the right?
Function.
A function. Is a number the same thing as a function? No, that's like saying is a noun the same thing as the sky? No, right? Okay, so these are not equivalent. Now they are. Okay, as we get going along, folks, you won't have to write the x equals, but for a little while I would like you to write x equals here, and in fact let's go ahead and write it over here too. just for a little while until you get comfortable with it. Okay, because come Calc 3, that's going to be exceedingly important to make sure you're keeping track of the variables there. Okay? Any questions about this? So, it seems like I'm splitting hairs here, but this is an important, if you don't get this concept down, you're gonna lose yourself in the middle of these problems. This type of object is a definite integral, which is a number, which means you cannot just give that as your answer, because what's that? An antiderivative, which is a function. A number and a function are not equivalent. Okay? Okay. So this is equal to, let me come down here where I can compute it. So this is equal to minus 1/3 times 2 cubed plus 4 times 2 minus parentheses minus 1/3 times minus 2 cubed plus 4 times minus 2. Well, let's see here. If I do this, it'd be 8. I'm cheating. This comes out to be 16/3 minus a minus 16/3. Folks, to be honest, I didn't really just compute those. Okay. What does that give me? 32/3. Okay. Now I did this third problem. We did this exact same problem 3 times. One, because I just want you to get comfortable with the notation. And this way you don't have to worry, you don't have to spend a lot of time thinking about the antiderivative, right? In each one of these, the antiderivative was the same thing. Okay? But there's one other reason why I wanted to do this example. How did this answer compare to our first answer? It was double that. Convince yourself. Look at this region right here. Look at that region right there. And look at this region right here. I've just added a symmetric half to this. Okay? By the way, this gives us a handy little property. Okay, so let's just add this somewhere if you can find some room. Suppose f of x is an even function. Okay, what does it mean to be an even function?
Means f of x and f of negative x equal.
Equal. Perfect. That's beautiful. That's the exact definition. Okay. Usually I don't get the definition when I ask for that. That's perfectly right. That's exactly what's right. Okay. Graphically, what's an interpretation of an even function?
Symmetrical.
They're symmetric how?
With respect to the y-axis.
With respect to the y-axis. Okay. They're symmetrical with respect to the y-axis, just like faces are supposed to be. Not like that. That's not what we mean when we say faces are symmetric, right? We mean like this. Symmetric with respect to the y. That's even functions. Symmetric with respect to the y-axis. Okay? Okay. So then if I ask you to find the integral from minus a to a of f of x dx, I'm asking you to find the area underneath the curve of 2 separate halves, but those 2 separate halves have identical area. So we could rewrite the problem as 2 times the area from 0 to a of f of x dx. And there's a nice little integral formula for you. Okay? That statement is just what we realized here. If I ask you to find the area from minus 2 to 2 of this even function, we could have just found the area from 0 to 2 and done what with our answer? Doubled it. That's what we're saying here. Give you a chance to copy that down if you need. Any questions on how that works? To be honest, this theorem right here, this little formula, sometimes it's called a theorem, sometimes it's called property, whatever you want to think of it as. It's not really a big time saver, but it's a little bit of a time saver. How come? Usually it's easier to plug zeros into these antiderivatives than most any other number. So that is a little bit of a time saver for you. Okay? But we'll get something similar in just a moment. All right, next page. So now let's do this again. Let's find the area of this shaded region. So let's look at this function right here. This is the graph of f of x equals x cubed. And let's find the area between 0 and 3. No. 0 and 2. Okay. Let's find that area underneath the curve. So I'd like you to do it. You've got all the tools you need. Go ahead and give that a shot. Check with your neighbors, folks, please. Once you've written out the definite integral, check with your neighbor. Make sure you're both on board, then move on. Okay. Resuming. We usually don't think about this, folks, but you should be thinking about this as x cubed times dx. Now, that times doesn't really matter once we do the antiderivative calculation, but do recall that that is what's going on there. Okay. Great. So, Veronica, help me out. What is the antiderivative of x cubed?
1/4 x to the 4th.
Okay, so that's the antiderivative. Can I just leave it like that?
No.
Yeah. So, Logan, what do I have to put there?
I forget the name of that line, but you put the line
Sure.
and then the 2 over 0.
Great. For a little while, I'm going to keep putting x equals just so we keep reminding ourselves of how that works. Okay. By the way, sometimes in a textbook, they might draw the line like that, I think. And they'll put 0 and 2. Or, sorry, other way around, 2 and 0. But that's, anyway, so you might see different notations for that evaluation bar. I don't really have a good name for it. I just call it the evaluation bar. Yeah, George.
What is that line called?
Yeah, I don't. Yeah, I don't have a really good name for it. I just call it the evaluation bar.
Okay.
Yeah, yeah.
So that basically evaluated at 2 and 0.
So this whole thing taken together means f of 2 minus f of 0. That's what the whole thing means. But I don't have a good name for what that bar is. I should do some digging around, but I don't. Most books don't have a name for it. Oh, good golly. Come on. Okay. All right, close enough. All right, great. Okay, so how do I interpret this expression right here? I just had it on the board. How do I interpret that? What do you say, Angela?
It's bracket 1/4 times 2 to the 4th.
Times 2 to the 4th,
Bracket
good.
Minus 1/4 to the 0 to the 4th.
Awesome. Okay, and that simplifies, let's see, 2 to the 4th is 16 divided by 4. That gives us what? 4. Oh, that's nice. Not always do these work out nicely. Okay. What does that 4 stand for? Is that the height of this function? Is that the height of this function? No, what is the height of this function here? 8. What does that 4 stand for?
The area.
The area of the shaded region. Okay. All right, I do want to show you this real quick, folks. You don't have to jot. We'll go through this again. But here was our x cubed function, right? And we were looking for this quantity right here between 0 and 2, right? Okay. Let me just show you graphically what we just did, and we'll get a better justification for this later. But we found an antiderivative of this function. Which antiderivative did we find? We found the antiderivative 1/4 x to the 4th, right? Then what did we do? We plugged 2 into the function, and that gave us the value. So we plug in a 2, that gives us the y value of what? 4. And then we also plugged in 0, and that gives us the y value of 0. What is the difference between these two numbers? The difference between those two numbers, their difference, this 4 minus 0, that is the area underneath the curve. That is what the fundamental theorem of calculus says. Okay, we'll talk more about that later, but that's what we did. We computed an antiderivative, and rather than computing an area underneath the curve, we looked at a difference in two functional values. Really interesting idea. Really interesting idea. We'll get back to that later. Oops. Okay, let's do this one more time. Okay, let's take the same curve. Let's find f of x. Let's say just x cubed. Okay, what am I asking you to do here, folks? it? Let's see. We'll do the work. But what am I mean, just literally, what am I asking you to do right here? I'm asking you to compute the net area underneath the curve between. So I'm asking you to find this net area right here. So let's do the work. This is 1/4 x to the 4th, evaluated from -2 to 2, which is equal to 1/4 times 2 to the 4th minus 1/4 times -2 to the 4th, which is equal to 4 minus 4, which equals 0. Does that make sense? Brandy, you're shaking your head. How come? Or you're nodding your head. Sorry, that was yes, it makes sense. How come?
Because you subtract it and it's the same.
What do you mean?
It's symmetrical with respect to the origin.
Ah, okay, I like that.
So, I don't know. It's,
Okay.
you
Well,
subtract one side and add the other. And
yes, that's what I'm after. How do we count this region? It's above the x-axis, so we count it as a positive area. How do we count this region?
Negative.
Then, by symmetry, what do we know about those two regions? They're the same. But one's counted positive, one's counted negative. Does it make sense that when we evaluate the net area, we get a net area of 0? Okay. So, here's one more little theorem. Okay. If f is a what type of function? What type of function was this?
Odd.
An odd function. Okay. Now, are all functions even or odd? Do they have to be one or the other? Most functions are neither even nor odd. So this is not necessarily a time saver for most functions. But every once in a while, it is. If f is an odd function, then the integral from minus a to a of f of x dx is what? 0. Because the positive regions, we don't know what they are. There might be many of them, there might be none of them. The positive regions will always cancel out with the negative regions. And we saw, you know, if you missed that, you just do the computation, and at the end you get 0, and you go, oh, duh. I should have seen that. Do people still say, oh, duh? Or is that old-fashioned? Okay? All right, oh, duh, we should have seen that, because it was an odd function to begin with. Okay. What would I like you to do now? I'd like you to work question number 9, all of them. Okay? So I'm going to turn you guys loose. We're going to work for about 20 minutes on this. Okay? I'd like everyone to pair up with somebody. Okay? Pair up with somebody. If you feel like going fast, you want to pair up with somebody that goes fast, that's fine. But find somebody to pair up with and work with on these. Okay? But go through them, and then I'll just come around and help you out. Logan.
A question on number 7. I noticed that the area was half the height. Is that purely coincidence?
That's coincidence.
It is?
That's a good. It's good to look for that. But that's.
Okay.
I've kind of picked some nice functions that are easy to work with, and so,
Yeah.
you know, there's patterns in numbers that are sometimes meaningful,
Yeah.
sometimes not meaningful.
I wasn't sure if it was like making some sort of triangle or something.
No.
Because I don't think I did the integral symmetrical, and then we were plus C. I did a plus C, but you don't have to write it.
Just a linear y.
Well, I did not.
X.
Yeah, it's just
It's like 45 minutes.
So would it be a constant 1 on
Yeah.
y-axis? Y equals 1? Or
yeah, I don't know. Or if it's just a
x?
Cotangent becomes 1.
Yeah.
And the second part becomes minus root of 3. And so it's just easy to pi over
So I
4.
guess that would just be
It's just 3 minus 2. Right.
So we're going,
What's the
negative 2 to 3 is
Seems to be a
going
pattern.
from this one. It would just be that one.
yeah, y equals 1 multiplied by 5.
So it would just be a straight
So you take
Hey
time?
folks, let me ask you a quick question. For this first one, we got an answer of 0. Does that mean it was an even function or an odd function? I'm sorry. Yeah, nothing like that. Notice that these limits of integration aren't the same, first of all. Okay? And second of all, there are ways you could have a non-even or non-odd function and still have them cancel each other out. Okay? All right. That's all. Go back to work.
cosine of whatever t which is 0.
Yeah.
Yeah, that's right.
Right.
Which makes it easy because if y was
So you would end up
something
with
stupid.
so if you just
12,
Well,
Yeah.
12
right.
is
Yeah.
multiply that by
Yeah. It's just one. Yeah. Just a one
make
there.
it a little bit
Oh yeah. Or we just have to carry it.
Oh, okay.
no, that's not.
So that's
No.
x to the negative 1. Right. Well, wait, yes. Absolute value. Yeah. So we have natural log of absolute value from natural log
Zero.
natural log of 2 minus natural log of 2.
I just left it like that. Yeah.
e to the power of 1.
I do too.
Yeah.
You don't.
Sorry.
So, with it being absolute value, if
What? Yeah.
that one, well, if the 2,
Hey folks, let's make a quick comment on number C here.
We going out? My buddy's coming to town.
domain,
Oh, cool.
Letter C, number C, whatever.
64.
yeah.
Let's make a quick comment on number C here. Somebody want to give me a real quick geometric interpretation of what we just calculated?
A line?
Quite a line.
That one where y equals 8.
Well, yeah, so this is, I mean, here we've got y as our independent variable, and it's not really clear what our dependent variable, I guess y is our independent variable, and who knows, we could have y, and we could just call this f of y up here. What does the graph of this function look like? Logan said a line, I agree. And what were we doing? We were computing the area underneath this curve between -3 and 5. How do you compute that area? Do you need this powerful integration tool?
No.
No, what's that shape? A rectangle with a height of 8 and a base of 8. And so what's the area of this? Actually, it's not even a rectangle. What's the area of this square? 64. That fits. Okay? So don't forget to see the trees through the forest or whatever that saying goes. Okay? All right, back to it.
Basically, the same.
And that is a track. It's 1 over x times dx.
Oh.
And then the derivative of 1 over x, I believe, is L absolute
Square
value.
is the antiderivative of tangent, right? I have no idea. Square the antiderivative of tangent. Oh, I thought tangent.
We're going to want to rewrite this.
Okay. Maybe because 1 over x is the same as multiplied by dx. So dx. Oh yeah.
So it's still x to the 1/2, right?
Because it's 1, but you can't
Plus
evaluate
x to the 1/2. Is the x to the 1 minus
Isn't that one right?
x to the 1/2 is x to the 1/2?
Yeah, this is technically.
Or you could do x to the first power plus x to the negative half. So it would be x to the 1/2.
Okay, so there's nothing, so it's whatever the ln of 2 is.
So proud of him. I actually know you give it. But you're plugging them.
Alternatively, x to the 2 over 2 minus x to the 1 over 2.
What is that? It's ln of 1 and 0.
Yeah, and so that's where x to the 3/2. Secant squared is the derivative of the bottom for x to the.
So that's why the antiderivative of secant squared is 10x. So
10 halves
dx and also the end is like, oh my god, almost looks like you're multiple.
So are you combining those?
What's that? These two? Yes.
The end two. Are you gonna combine those? Try to make
If
those
they're
one
both
X?
halves, we'll see. Yeah, we'll see.
I knew it was
But I don't think we can, so this is 3 halves, 6 halves minus 3 halves is x to 3 halves.
Minus x.
No, it's not right.
and I like knew that.
X to 2 halves, that's x to minus 1 half.
You got it wrong in the test? Yeah.
So I don't think I can combine those, right?
No, I just meant like the top, the numerator, the top X and the bottom X of each of your division ones. That's what I meant.
Oh yeah, so I divided this into both terms here.
And then you further combined them.
Then I went ahead
So you
and
could
further-
use your power rule.
Using just working with powers there. Yeah.
I put 1 over 1/2 power.
Well, sure. So this is x to the 2 halves over x to the 1 half.
Okay, makes sense.
Yeah.
Are we gonna get a better rule for that eventually, or no?
No, then the power rule? No, the power rule is about as nice as it gets.
Was it like
Good question.
Yeah.
How did you go about doing number F?
Okay. So the first thing to recognize here is that we have d over x, but that's the same thing as 1 over x times dx. Okay. I think this is silly. Yeah, folks, for number f here, look at the way this was written. Okay. I wrote it that way because that's how it will often be written in a math textbook. Because it saves them about a millimeter of space. That's why they write it that way. Okay? It's pretty silly for all the semesters I've had to stop and explain why does it look that way. They saved their millimeter, but boy, they cost me. Anyway, I mean, it makes more sense to write it this way, but do you agree that I could write it that way? Okay. So then, what function, when we took its derivative, gave us 1 over x? The answer was the natural log of whom? Absolute value of x. Do you need that absolute value? Generally, yes. Okay. Evaluated from the 2 endpoints, and of course, what's the natural log of 1? Natural log of 1 is 0.
If you do the higher before, if you do that in unit circle, it's a special right triangle, so it should be root 2 over 2, or 1 over root 2 over 2. Yeah, that's my hint. So it would end up being 2 over root 2. So, but it's best to execute on No, because it's 1 over 2 over root 2. And then you copy dot flip. So you have 2 over root 9. Oh. So, it's, so you have 2 root 2 over 2. No, it's just, so it's just 2 over root 2, because the root 2 over 2 got canceled by the other 2. So you do by 2 over root 2, because you multiply the top and the bottom by root 2. But this times this is just
Watch my addition, folks. Let me know if you're not getting the same thing.
okay.
Again, the main work is to go from here. You know, this is the main step, the critical step.
Oh, he has a plus.
Double check I did that right. Added 1, so it's 3 halves divided by 2.
Yeah.
Added 1, so it's 9 halves divided by 2. Added 1, so it's 1 half.
And the bottom. So these two
Oh, this is because of the manipulation of 1.
Yes, we copied off these two. The top and the bottom.
Oh, yeah, I'm just saying, if you don't want to leave this on the edge.
Or, yeah, except this doesn't matter, so, yeah. He did 0.
Folks, anyone have any questions? Anything they want to look at? Should I just come around? Pause this. Just come around and see what you got. I now want to work harder problems. Okay. hopefully at this point you see that these problems are all exactly the same up to what? Up to finding the antiderivative, right? And we've learned some tools for finding antiderivatives. I'd like to now give you a new tool that we haven't learned before. This new tool for finding antiderivatives, this new tool is undoing the chain rule. And we will have a whole sections lesson on how to undo the chain rule in a little bit here. Okay? But I feel like we've done the work that I could actually go ahead and show you some of these problems, and that's just going to expand your tool set, your skill set. Okay? When you get stuck in an integral problem, you start running through your toolbox. Okay? First thing is it an elementary antiderivative? Is it like secant squared of x? Oh, I recognize that. That was the derivative of the tangent. Okay? Or is it something where I can rewrite it so I can use the power rule on? Right? Those are the first two things you should always check for. Okay? The next most common thing to check, and the first kind of the big tools for finding antiderivatives, is something called a U-substitution. Okay? And a U-substitution, as I said, is used for undoing the chain rule. It's a way to undo the chain rule systematically. So to undo the chain rule, what you're going to be looking for is an expression and that expression's derivative up to a constant. Okay? Well, I'm looking right here and I see this expression. Do you see this expression right here? X cubed minus 3x squared. I also happen to see that expression's derivative. Do you see that expression's derivative? Yeah, what's its derivative? It would be 3x squared minus 6x. That's this term right here. Okay? So this is going to be a u, and this is going to be a du. So this is how we do this. Okay? So it takes an eye, right? It takes a little bit of an eye to spot both an expression and its derivative, and they're going to get harder as we go through. Okay? But we're going to do a bunch of them together, and this is going to lay the groundwork for where we're going in the next few sections. Okay? So I'm going to write let u equal x cubed minus 3x squared. I've been trying to get you ready for U-substitutions the whole course, to be honest. We've been doing them throughout the course, but now we're going to do it with this anti-differentiation technique. Okay? So if I went ahead and took the derivative of both sides with respect to x, I would get du dx is equal to what? 3x squared minus 6x. Okay? Now, I'm now going to use a trick that we sort of saw when we were working with differentials. I'm going to go ahead and formally multiply both sides by differential x. And if I do that, I get the statement that du is equal to 3x squared minus 6x dx. Okay. Any questions up to this point? Okay. I'm not expecting you to master this today, but I want to give you some exposure to it so you can go through and start working all remaining problems. Yeah, Jack.
Would there be parentheses around 3x squared minus?
Yeah, you know, I should be more careful and put parentheses around there. There should be parentheses around it. Okay, this next part I'll just mention now. It doesn't apply here. I now look at what I have and I say, does this exactly agree with all the expressions in here, or is it off by some constant? And if it's off by some constant, I adjust my substitution. Okay? You'll see what I mean in some later problems. Actually, in the next problem. Okay? Okay. So, now I'm ready to rewrite this thing. I'm going to take the antiderivative, and then look what I'm going to do here. Right here, in fact, let's put this in. Right here, that's what I've called u. Right? So I've got u to the 5th power, right? Everyone see that? Okay. And then, this part's the trickiest part. I've got this expression times this expression, right? Well, there it is. That expression times that expression. And so what could I call all of that? I could call all of that du. So by doing a U substitution, we sort of, and this is really just a mental, this is just a systematic trick to make things easier on the eyes. We could have looked at that problem that way to begin with, but it's hard for us to do so. This is just the antiderivative of u to the fifth du. Well, what is it? What does that evaluate to? It evaluates to 1/6 u to the sixth plus c. Why is there a plus c on this one? Because I'm back to doing indefinite integrals. I'm just looking for the antiderivative in this problem. We'll worry about doing limits of integration later. Okay. But u wasn't, this part always sounds like I have poor English, which I do, but this makes it sound relevant. U wasn't the variable you were asked to solve for, was it? No. Well, what was u? Well, u was x cubed minus 3x squared all to the sixth power plus c. Everyone see what we did? The phrase is we back substituted what u was holding the place of. All right, what I'd like everyone to do is check my answer. I'm claiming that when I take the derivative of this, I should get this. Check my answer. Nobody's writing. Check by writing, folks, unless you're the cat's meow at doing math in your head. I can't check that in my head. So I'm going to take d dx of 1/6 times x cubed minus 3x squared to the sixth power plus c. Okay. For the first term, I'm going to first apply the power rule, right? The outside piece is a power function. So I apply the power rule, and I get 1/6 times 6 times this whole mess, all to the subtract 1 from the exponent to the fifth power. But what? The expression inside the sixth power here was more complicated than just an x, so I've got a chain rule, right? So that gives me 3x squared minus 6x. And then, of course, what's the derivative of the plus c term? Always plus 0, which is why it never shows up again. Okay. Do you see why we do a U substitution? I said this before. A U substitution is done to undo the chain rule. Okay. It's a methodical way of undoing the chain rule. All right, let's do another one. Actually, we're just going to work these all together. Okay? All right. This is a little bit harder. I'm running through my rules. Is this a basic antiderivative? No. Sort of looks a little bit like arctangent, but no, arctangent had a, no, not quite. It was x squared plus 1 in the denominator, and you couldn't have anything in the numerator other than a factor of 1. Okay. So, it's not an elementary rule. I don't think I could rewrite this and use the power rule on it. Okay, there is a way you could break this down. I don't want to get into it. Called partial fraction decomposition. You'll learn that in another class. Okay? But rather than doing that, let's just go ahead and do this U substitution. So what am I looking for? I'm looking for an expression and that expression's derivative up to but not necessarily including the constant. Okay, this takes an eye and this takes some practice, and you'll get both of these over time. I'm going to let u equal x cubed plus 3. Jillian.
Why did you pick that versus x squared?
Well, what's the derivative of x squared?
2x?
2x. Do I have just an x factor floating around? No. But let's check this. When I take the derivative of this, what do I get? I get 3x squared. Do I have an x squared factor floating around? Yes. So Jillian asked the question, how did you know to do this? Because I've done a million of them. Okay? But over time, you get better and better at this. Okay? So I'm just showing you some examples, and you're going to go home and try some examples. Okay? All right. This next step, I'm going to multiply both sides by dx. Folks, going forward, I will skip the middle step and I will just go from here to here, because that part always works out the same way. So I'll write u equals this, so du equals this. Okay? Now, this is where the u substitutions get a little bit harder, folks. What would I like to replace du with? What would I like to have du take the place of? I'd like to have it take the place of x squared dx. Do you see that? But I'm off by a factor of how much, Brandy?
I was spaced out.
I know, I saw it. Okay, I'm off by a factor of 3. Okay, so what am I going to do? I'm going to go ahead and multiply. I'm going to take that 3 over to the other side. So that tells me that 1/3 du is equal to x squared dx. By the way, if you learned u substitutions before, if you've happened to had a calc class before, you might have learned how to do these differently. Everyone does them their own way. Okay, this is how I do them. Okay, now we are ready to do the u substitution. So, what am I going to write in place of x cubed plus 3? I'm going to put a u there. Then what am I going to put in place of, notice this is why you get to think of this as all by multiplication, x squared dx. What am I going to put in place of this x squared times dx here? I'm going to put 1/3 du. Which I could rewrite as 1/3 times the antiderivative of 1 over u du. Which is equal to 1/3 times what? Everybody? Natural log of absolute value of u plus your obligatory constant. Folks, it breaks my heart if you get to here and you say, well, I've got an answer, and you walk away from it. Because what was our original function given in terms of? What variable? X. What have we said the answers in terms of? U. But u wasn't the variable you were asked to solve for, was it? Well, what was u? Well, u was what? X cubed plus 3. Folks, every time you do a u substitution problem, please check your work. You will get a better understanding for how the u substitution works. You'll get better at it by checking your work, by seeing how a u substitution is undoing the chain rule. Okay? So I'm not going to do this here because we got to keep moving, but I want you to practice that. Okay. Moving on, because I just want to get through more of these problems. All right. This one requires a little bit more of an eye. Let's first rewrite it, because I already know what the answer is. Let's first rewrite this as the natural log of x times 1 over x dx. Ooh, now it looks a little bit easier on the eye, right? I'm looking for an expression, and so this is a u substitution procedure. I'm looking for an expression and that expression's derivative. What is my u going to be in this problem? Don't say it out loud. Everyone write down, right? Let u equal, and then write du equals, and fill those 2 lines in. Max, what'd you put for u?
X.
X?
Oh, wait.
Well, I could do that.
I was looking
And then
for
what would du be? It would just be 1 dx.
Yeah.
But then when I do the substitution, what would I end up with? I would end up with the integral of the natural log of u times 1 over u du. Have I made my problem any easier?
No, it's the same thing.
It's actually the same thing, right? So what Max said is a great thing to do. If you're stuck on these problems, take a guess. and then fill it in and then see whether it's making your life easier. Don't spend all of your time wondering about this. Just make a guess and then adjust. Okay? All right, do we have another guess for what our u should be?
Natural log of x.
Daniel says the natural log of x. Oops, that's just regular natural log of x. Good. Why did you pick that?
Well, for starters, it's the only other option that we kind of have, and
Well, I could have picked 1 over x, right?
yeah.
So what are we looking for in a u substitution? We're looking for an expression and that expression's derivative. What is the derivative of natural log of x?
1 over x.
Which shows up in the problem as well. That's the hint. Exactly. Exactly. So, in fact, let's go ahead and do this. So then we write du equals 1 over x dx. This is an example of what I call a perfect substitution, like our first problem. Whereas our second problem wasn't quite a perfect substitution. We had to do some adjustment. Okay? So what do? Well, I look up and I say, okay, I'm going to replace this with a u. Okay, I'm good with that. And then I'm going to replace the rest of it with a du. Everybody's being accounted for, so I'm ready to make the substitution. So go ahead and do the substitution. Very similar to a college algebra technique, right? It's a college algebra technique for solving equations that were quadratic in form. I think they even made you use the letter u in it. Remember doing that? Sorry, I've forgotten. It's okay. All right. This was hard on the eyes. This was a little bit easier on the eyes, but this, poof, no problem at all. Okay. Jillian, what do we get for an antiderivative of this? So this is understood to be u to the what power?
1.
U to the 1, so I'm going to use my power rule on it.
So 1 over 2.
1/2
U squared.
u squared.
Du.
No.
Oh.
Plus c, right? Where did the du go? The same place that the integral symbol went. Okay, when we evaluated the antiderivative, they kind of got used up. Okay, we'll talk more about that. You'll actually see what happens to it in just a moment. In a moment. Next several hours. Okay. Okay. Are we done with the problem? Thomas, what do I still have to do?
You have to substitute u.
What was u?
Natural log.
Folks, what is the u substitution used for? It's used for undoing the chain rule. Check your answer. Take the derivative of that. You would have to do the chain rule, right? Do you see it? Okay. All right, let's look at lemma m here. M is hard for two reasons. One, it's not going to be a perfect substitution. Why else is m going to be hard? What have the first 3 problems been? They've all been indefinite integrals. What's this one? Definite integral. It's our first time doing a definite integral u substitution problem. Okay? We handle these slightly differently. We're going to handle these slightly differently. Okay? Rather than back substituting what u was, because we're not after a function here, right? We're just after what type of object? A number. We're just after a number. So rather than back substituting what u was, we're going to adjust everything in terms of u, including our limits of integration, and then we'll just evaluate and we'll get a number. You'll see what I mean here. Okay? All right. Here we go. Let's roll up the sleeves for this one. Just kidding. All right. This looks like a huge mess. I'm trying to find what function, when I took its derivative, gave me this expression. It looks like a huge mess. It's not an elementary rule. I can't use a power rule with it. So my next option in my toolbox is a what? U substitution. How do I know if a u substitution is going to work? I look in there and I look to see if I see an expression and that expression's derivative. Okay. All right, I'm going to go down the wrong street for just a moment. I'm going to say let u equal 2 cosine x. Then du would equal minus 2 sine x dx. But these two things are being what together? Multiplied together. That's not going to help me out. Okay? Because I can't have the dx be up there inside of the exponential function, right? Or the du be up there. Okay? So I made a choice, and it wasn't a bad one. Right? I mean, it was true that the derivative shows up there, and we've got the right answer up to a constant, but it doesn't help me with this substitution step. Okay, so what should I let u equal? Should it just be 5 sine x? Yeah. If I just did 5 sine x, then I would still have eventually I'll have a u minus 4 up there, and I'm not really sure how I would do that. Actually, it wouldn't be too bad. But anyway, you want to grab everything up, including constants, when you do these u-substitutions. Okay? So then what is du? Du is equal to 5 cosine x
Times it?
dx. Do not forget that dx. That is the essence of the substitution. You can always replace a number with any other symbol, but what you have to, once you do that, you have to move everything else accordingly. Okay, so it's not just that we're replacing this expression, we also have to replace anything that depends on it, like that dx. Okay? So you need that dx there. All right, now, this isn't a perfect substitution. Why not? Because I don't have a 5 cosine, right? What do I have? I've got a 2. So what should I do with this 5? Let's divide it on over. So that gives me 1/5 du is equal to the cosine of x dx. Yeah?
So I'm wondering what happened to the negative 4.
When I took the derivative of it, what's the derivative of minus 4? That's 0. No, it's a good question, right? So that's why it's precisely that. That's why I usually scoop up as many constants that are next to it when I do this u substitution. Yeah, great question. Okay. All right, folks, let me get started here, but we've still got more to go with this u substitution. I'm just going to, for right now, write this as an indefinite integral. Okay? So in place of e to the 5 sine x minus 4, I'm going to put e to the what? E to the u. Everyone okay with that? Let me just show you. This u replaced all that. Okay? Now this only works because this is all one long string of multiplication here, right? So in place of the cosine x dx, that's the cosine x dx, I'm going to replace all of that with 1/5 du. Okay? Oops, I should have done that in a different color. Let's do red. What on earth? Okay, my color. I don't know. There's no color scheme there. Ignore the colors. Okay? Anyway, in place of this expression right here, I'm going to replace it with 1/5 du. Okay? So I've got the 2. Nobody replaced the 2 there, right? That 2 is still there. And then we've got 2e to the u, and then in place of this cosine x dx, I'm just going to put the 1/5 du. Could I put that 1/5 anywhere in this string of multiplication? Yeah, I could have put it anywhere. In fact, if I were doing the substitution my first time through, I would have just put 2 times 1/5 e to the u du is how I would have written it to begin with. Okay? All right.
Why not 2/5?
Yeah. Could you write it as 2/5? Certainly. Okay. Certainly. Okay. Now, why else was this problem harder? So it wasn't a perfect substitution. So there was this step right here where I said, oh, I don't have a 5 when I look up here, so I better take that 5, that constant, over to the other side. There was that step there. What else made this harder? We haven't addressed it yet. heard it?
Definite.
This is a definite integral. We've got limits of integration. But look at, we've given ourselves a formula for how to adjust things in terms of x to things in terms of u. By the way, it might be helpful up here to write x equals 0 and x equals pi over 2. As we sometimes have, right? So now I'm doing a u substitution. Well, when x equals 0, what is u? U is equal to 5 times the sine of 0 minus 4. What was that, Mia? U is just going to be negative 4. Everyone see what I did there? No, I need feedback, folks. I need feedback. If I lost you, you need to tell me, because then I didn't do my job. I take silence for I get it, and I know I shouldn't, but if you don't tell me something, I can't. Yeah, George.
Can you explain it again?
Yes. Okay. So this not only is how we're going to replace the variable, this expression up here with u, it is also a way for adjusting the limits of integration. So what was one of the values that x took on in our limits of integration? It was 0. So when x is 0, what did I do? I took the substitution formula. I took this substitution formula right here, and what did I do? I replaced the x with a 0 and then cleaned it up. What's the sign of 0?
0.
0 times 5 is 0 minus 4, so then we're going to replace the u here with minus 4. Okay, George asked the question. We clarified it for George. Who else has this question?
Is that why you said earlier it wouldn't have been that bad if you left the negative 4 out?
No, you did. You didn't want to leave the negative 4 out. That's why it would have been kind of problematic, partially. Thomas.
How did you know not to evaluate it at pi?
What's that?
So like when you said when x equals 0,
Uh-huh.
how did you know not to do pi?
Oh, great. We're going to do it right now. So you tell me. When x equals pi over 2, how are we going to find u? We're going to say u equals what?
5 sine pi.
5 sine of pi over 2 minus 4, right? And what's sine of pi over 2? 1 times 5 is 5 minus 4 is 1. So what's my upper limit of integration get adjusted to? 1. So everyone see how we adjusted both limits of integration as well as doing the u substitution. Okay, folks, I need your 100% attention here. Make sure you got that. Okay. Does anyone have any questions on that? I got 2 good ones. I need some more. Jack.
Does the upper limit always have to be a larger number?
No, it does not. We'll talk about that. We'll talk about that in another section. But basically, if they're off by values, you can just there's a trick you can do. But even if not, you could just go ahead and evaluate it anyway, because there's nothing that said. Yeah, we'll talk about that. It's a great question. Brandon, did you have a question? Nobody else has questions on that? I don't believe you. All right. So this gives us 2/5 times the integral from u equals minus 4 to u equals 1 of e to the u du. But what is the antiderivative of e to the u? So it's just 2/5 e to the u evaluated from u equals minus 4 to u equals 1. Which is equal to 2/5 times e to the first minus e to the minus 4. And there's our answer. Okay. Folks, did I ever have to back substitute in this problem? No, how come? Because I adjusted the limits of integration along the way. Why? Because I wasn't after a function here, right? This question didn't say find the antiderivative of our original integrand. It didn't say find the antiderivative of this. It said what? Find the net area underneath the curve, which should be what type of object? A number. Did we find a number? Yeah, don't Don't be rude. Yeah, it's ugly, but we don't have to say that. Okay? We found a number. Okay? We found a number that represents the area underneath this curve. Okay. Let's do another one. Okay. All right. I'm thinking I'm going to have to do a U-substitution on this one. Now, it's almost an arc sine, right? This almost looks kind of like an arc sine, or maybe an arc cosine, because you got that square root of something squared minus x squared. But what? What's preventing you from being able to do that? The x in the numerator. Okay, so it's not an elementary antiderivative. Okay, so that's one of the hard parts about antidifferentiation, right? One extra factor somewhere completely changes the game, right? That's why this takes so much work. Questions on that? Okay. All right. Was there a question?
Why can't you just break it up into like two separate?
Oh, great question. So can you break up? So you can break up integrals term-wise. You can't break them up factor-wise, right? That's kind of the same thing as asking, when you have the derivative of a quotient, why don't you just take the derivative of the numerator over the derivative of the denominator? You can't. You have to use the quotient rule. Okay? So we don't have the equivalent of how to undo a quotient or how to undo a product yet. We will learn something like that in Calc 2 when we learn the integration by parts, but even that's not perfect. So yeah, you cannot, this is not true. You can't say that's the antiderivative from 0 to 3 of x dx all over the antiderivative from 0 to 3 of the square root of whatever, 25 minus x squared dx. You cannot break it up over the numerator and the denominator. Now, if they were terms, you could break it up over terms. Or if there were differences, you could break it up over differences. Great question. Okay. So, it's not an elementary rule. I don't think I could set this up for the power rule, so I'm probably going to have to use a U-substitution. Okay? So what am I looking for? I'm looking for an expression and that expression's derivative up to a constant. What's an expression that shows up as well as its derivative? Yeah. We're going to let u equal 25 minus x squared. Folks, if you don't see it right off the bat, put something down and then check. Take its derivative and see if you'll be able to do the substitution that you want. Just put something down. Okay? All right. So then that makes du equal to what? Negative 2x dx, right, folks? I was a little concerned about how silent you were. What did I just do? Anyone want to talk about that?
Took the derivative
All right.
of 25 minus x squared.
So what I'm going to do is I'm going to take the derivative with respect to x. So du dx is equal to what? What's the derivative of this expression? Oops, that's not right. What's the derivative of this expression? Minus 2x. Everyone okay with that? Okay. This is just like if I wrote y equals 25 minus x squared, then what's dy dx? What's the derivative? Minus 2x. Everyone okay with that? Okay. But then what I do is I do this little formal step of multiplying both sides of this equation by differential x. And that gives me du equals minus 2x dx. Okay? You are welcome to always show this middle step, but I will generally just go from here to here in one step. Because this part always works out to be this part, and there's no, yeah. Okay. Questions on that? We feel better? Any feedback, folks? Give me thumbs up, thumbs down. Curtis? Okay. All right. Now, I look up at where I'm going to be doing the substitution, right? You can kind of see where this is going. I'm gonna go ahead and erase this if that's okay. Well, I did it anyway, whether it was okay or not. Okay, so you can kind of see how this substitution is going to go, right? We're going to have over the square root of u, right? And we'll be able to replace, there's where we'll do with the dx, and we'll be able to do something with that x factor, but what? We're off by a factor of what? -2. So what do? I divide that factor over to the other side. Okay. I'm going to go ahead and put the -1/2 out front. Do you mind me doing that? It's just being multiplied, and I can pull factors out of integrals. Okay. And so we'd have just 1 du. Okay. If you don't believe me, just put all this in here and multiply that top. It would be -1/2 times 1 times du, which is exactly what we've got here, which is exactly what we replaced the x dx with. Spend some time thinking about that. It all has to just do with multiplication. You can rewrite, multiplication is associative and commutative, so you can move it around as you need. As you wish. Okay, what else do we have to still do on this problem? What do you say? Who am I going to talk to today? Andrew, what do you say? What do we still have to do on this problem?
Oh, you have to substitute for the u.
What do you mean?
Substitute the 25 minus x squared.
So we did that, I think.
Oh, yeah. Oh.
Yeah.
So you have to take the indefinite.
We could do that because this is an indefinite integral. Really, what type of integral should it be?
Oh, you bounded rooms here.
So it's definite integral, so what do we still need to do? So let me just say, this was x equals and this is x equals, right? What do I need to do?
Find the bounded for u.
Yeah, I need to, and the phrase we use is we need to adjust the limits of integration. Okay, I've got a little more room this time to do this, so hopefully this part will be a little more clear. Okay, what was my upper, so who had trouble last time when I adjusted the limits of integration? Maybe somebody admit they had trouble, because then I can work with you.
You just basically
Yeah, Daniel. What was our lower limit of integration?
0.
Okay, so we write when x is 0. Okay, what's our formula for getting from u world or from x world to u world? This is the formula that we came up with. It's going to translate between the two, right? So when x is 0, u would be 25 minus what?
0.
Minus 0 squared. So what is our lower limit of integration going to be? 25. So then we put u equals 25. So we changed our lower limit of integration from u equals 0 to u equal, or from x equals 0. Slow down. From x equals 0 to u equals 25. Okay. Who else is having trouble with this adjustment? Not that bad once you learn it, I promise, but I completely understand why it's confusing the first few times you see it. Who else wants to talk about it? Yeah, Avery.
Do you have to write the u equals on the new?
You do not need to write u equals, that's implied, but I think you should for a little while, just so you get comfortable with the idea of, oh, I am adjusting my limits of integration because they are from different variables. So I wouldn't mark you wrong for it, but I think you should write it until you're bored with writing it. Okay, once you're bored silly with writing it, you can stop. Okay, well, nobody has a question. All right, I'll do the other one. When x equals, what was the other limit of integration? 3. U is equal to 25 minus 3 squared. U would be equal to 16. So this is going to go up to u equals 16. Okay. Okay. Jack asked last time, he said, what happens when the lower limit of integration is lower or is above the upper? That's not a problem. We could go ahead and evaluate this as it is, and everything would work out just fine. Okay, it's sort of like it doesn't matter when you're doing your 2 points in the slope formula as long as you're consistent. Kind of the same thing here. However, we do have a nifty formula that we'll talk about at some point down the road here. We do have a nifty formula that says if you want, you can adjust the limits of integration. See what I did there? I adjusted the limits of integration if you change the sign on the integral. Specifically, what's not there any longer? The negative sign. Okay? So you can flip the units of integration if you change the sign on the integral. Okay? We'll talk about why that is later. Of 1 over the square root of u du. All right, folks, I'm flying through this material. This is section 5.5 right now that we're going through. Going through it fast. I feel like we can all get through this, okay? But it only works if you're asking me questions. Yeah, Journey.
Would you get the same answer if you kept the negative one half inside of the integrand?
Yes, but you would. So if you had this minus 1/2 inside the integrand, and you flip the integration, then you'd stick a new negative sign there that wasn't there before. Yeah. So the property. It's a great question. The property says if you have the integral from a to b of f of x dx, doesn't matter what a is, doesn't matter what b is, doesn't matter if a is bigger than b or not. It just says if you flip the units of integration, then you change the sign on it. Yeah, great question. Other questions? Yeah, Darcy. Sorry.
Could you say again how you got the 1 on the top, 1 over root u?
Well, yeah. Let's see here. I've got such a stinking mess. All right. So at some point we started out with this. We went from I think it was 0 to 3 of x over the square root of 25 minus x squared dx. And then our substitution, I just need a little more room. So our substitution was u equals 25 minus x squared. So we said du was equal to minus 2x dx, or minus 1/2 du is equal to x dx. Okay? So at this point, there's lots of ways I could do the substitution. So one way to look at it is if I rewrote the original problem like this. See, I think we went from 25 to 16. Then when I do the substitution here, I'm going to replace x dx with minus 1/2 du all over the square root of u. How's that work? So it's just a question of what makes sense, on what's easiest for your eyes to see. So I said, okay, let's take a line and put this dx up top like we sometimes do, because now I've literally got this expression, and I'm going to literally replace that exact spot with that. Okay? But by all of our properties that we've worked with here, we could go from 25 to 16, and then where do we usually put the du? We usually put it over here, over the square root of u. And then what can I do with constants? They can factor out. Well, at this point, what do I need to put right here? It's right here. Negative 1/2. So this is a fraction, but when I've divided everything out of the numerator, what needs to go there? A 1. Okay. Then our next step, folks. So I'm just going to pick it up here. Our next step was go ahead and change the limits of integration, or flip the units of integration so we get 1/2. What's that? No, you do not. No, you do not. But you should practice doing it so you get comfortable with it. Okay. All right. So now we're down to just taking the antiderivative of this. This is a little bit tricky. What should I do? I should go back and write it as a power. So I can use my power rule on it, right? Logan?
Oh, I was just stretching.
Just stretching?
Sorry.
All right, no, that's all right. Okay. So let's see, this would be 1/2, and now I'm going to add 1 to the exponent, divide by the new exponent, evaluated from 16 to 25. Which gives us u to the 1/2 evaluated from 16 to 25, because factors cancel. So we end up with the square root of 25 minus the square root of 16, which comes out to be 9. No, it doesn't. That's a lie. Excuse me. course. So how did I get this 2 over 1 here? So I added 1 to the exponent, so I got 1/2, and then I divided by that new exponent. What happens when you divide by 1/2, Max? Yeah, sorry.
Yeah.
What happens when you divide by 1/2?
It becomes a greater number.
It's the same as multiplying by 2 over 1. Okay. Okay. That was a tough U substitution. Okay. We will get more practice with those. We'll spend an hour specifically working on just U substitutions down the road here. Okay. All right. I just want to keep moving. Here's another topic. How do we find the average value of a function? Okay. We'll spend some time talking about where this comes from, but for right now, let me just give it to you as a formula. The average value of a function, meaning the average y value that it takes on. Right? So if, let's say the function gives you the temperature at any time x. So you plug in x, you plug in the time, and it gives you the temperature. You might want to know what was the average temperature over that day. Right? So if you want to know the average value of the function, you're going to find the net area, f of, let's put x, f of x dx. Okay. You're going to find the total area, and if you take, sorry, by total I mean net here. That's kind of misleading. But you're going to take the net area, the area that you wanted, and then you're going to divide it by your length. Because if you take the area of a shape and divide it by its length, you get the average height of that shape. If you take the, so again, I'm going to use the word total, but I'm using it in a, just meaning because I want to talk about the whole thing. If you take the total area of a shape and divide it by its length, you get its average height. So how do you divide it by its length? You multiply it by 1 over b minus a. That's how you find the average value of a function. Okay? So let's look at our sine curve. Our sine curve on the interval from 0 to 2 pi looks like this. What should be its average height? Sometimes it's above the x-axis, sometimes it's below the x-axis. In fact, it's perfectly balanced. The average height should be 0, and we'll see that. Sure enough, if I asked you to compute the average value, you would do 1 over 2 pi minus 0 times the integral from 0 to 2 pi of the sine of x dx. But that's equal to 1 over 2 pi times, what's the antiderivative of sine? Careful. What's the antiderivative of sine? Negative cosine. Evaluated from 0 to 2 pi. But that's equal to 1 over 2 pi times minus the cosine of 2 pi minus the cosine of 0. Which gives us 1 over 2 pi minus 0 plus 0, which regardless gives us 0, which is the average value of the sine curve. Okay? That wasn't a very exciting result, but I'm going to stop that there. Okay? That's how you compute the average value of a function. Okay? Okay. I have one more, did everyone get that? I've got one more thing I want to show you. Got one more thing I want to show you. If you were to look at this curve right here, let's see here, I could factor this as 4x times x squared minus 6x minus 8. So this factors to be 4x times x minus 4 times x, oops, that should be plus 8, minus 2. So the graph of this curve looks something like this. Okay? Where this is at 2 and this is at 4, and that's at 0. Okay? Let's look at this question. Here I'm asking you to find the total area between 0 and 3. Okay? So I want you to find this, and I want you to find, here's 3 abouts. I don't know if that turning point's right in the middle there, but there's 3. Okay? Now, what's the difference between this and the word I've been using? I've been using the word net. When we use net, how do we count this area underneath the curve? We count it as negative. But if I want total area, if I literally want to carpet this region and this region here, I don't want this to cancel with this. I won't have enough carpet, right? So I want to count this as positive. So all I have to do to find the total area is to break it up. Okay? So the total area, I'm going to write as the integral from 0 to 3 of the absolute value of f of x dx. What did that just do? It just flipped all the regions below the x-axis above the x-axis. So now my definite integral, just as I normally use it, will count everything as positive. But to save time doing that, I need 1 more minute. To save time doing that, I'm going to go from 0 to 3, I'm going to go from 0 to 2 of f of x dx. What will that count? This part right here will count this part right here. And does it need to, do I need to worry about whether it's positive? Well, it's already going to come out to be positive, right? Then I'm going to subtract from that. Let me do that in a different color. Then I'm going to subtract from that the integral from 2 to 3 of f of x dx. Why did I subtract? That was just finding this area right here, which is counted how?
Negative.
As negative. And so how do I make it count as positive? I put a minus sign in front of it. That's just common sense, right? If you want to get the total area, you break it up into subregions. Anything that was below the curve, you change the sign on it to then make it positive. Now that involves you knowing what the curve looks like, right? Or at least knowing where it changes sign, which you can do. All right, folks, thanks for your patience. Please, what I need everyone to do, because it'll be due on, it'll still be due Monday night, is I need everyone to, over the weekend, watch the 5.1 lecture.
The net area